Good afternoon, everyone. Welcome to our Hackathon Showcase for 2021, Virtual Hackathon, our second year in the running. First, before we start, I'd like to thank Pocket Health for sponsoring our initiative, and thank you, Pocket Health. But next, I want to introduce our judges. We're very fortunate to have 6 judges with us today. And when I introduce you, if you don't mind just saying hi, that way Zoom will put yellow rectangle around you and let everyone know who you are. First, we have Dave DeBokark, ePatient Dave, who is a patient empowerment evangelist and chief patient officer at Pocket Health.
Hi.
Sorry for butchering your name there. Next, we have Kevin O'Donnell, who is a senior research and development manager at Canon Medical Research.
Hey, video technical difficulties, but hello.
Next, we have Dr. Amin Korchi, neuroradiologist and chief medical officer of Cerebro and director of imaging centers at Switzerland.
Hi, thanks for having me.
Next, we have Chris Havey, Principal Clinical Imaging Business Development Manager at Amazon Web Services.
Hi, everyone.
Chris. Next, we have Dr. Walter Wiggins, Clinical Director at Duke Health Center for Artificial Intelligence in Radiology.
Hi, everybody.
And next, last but not least, we have Mr. Herman Oosterwijk, who is an expert trainer and consultant working for OTEC.
Hello, how are you?
And I am Howard Chen. I work for Cleveland Clinic. I am your host for today's event. I also want to thank all our mentors, our co-heroes, domain experts. Without your help, this project would have been relatively boring because we can't get anywhere. So thank you for all your involvement and for being active on Slack and helping our hackers so that they'd be able to present the projects. Before we get started, officially, I want to lay out some ground rules. So here are the rules. Every team, there will be 8 teams that are competing today. A 9th team, so the 9th team would not be for a competing entry, it would be just sharing the work, but 8 teams competing, 9 total. There will be 8 to 10 minutes per team for presentations, plus 1 to 2 minutes for judges, questions, and discussions. That gives us a little bit of buffer at the end in case some of those sessions run long. I know 1 minute for Q&A usually doesn't work that way, but that's what we have for you. I will be keeping time, so if you hear me interjecting in the Q&A, it's not because I don't like your project, it's because we really do have to move on. For the audience, if you're not presenting and you're not one of the judges or Mohanan or myself, you have the option to vote for the Audience Choice Award, and the link will go into the chat. And what I will do after each session is to remind you of the names of the team and the project, so that if it is one of the projects you really like, please do vote for it for the Audience Choice Award. The winner for both the judging from the judging panel as well as from the audience will be announced at a SIIM membership meeting on Tuesday. That's next Tuesday, the 25th of May, 6 to 7 o'clock Eastern time. Also, if you follow Mohanan, you will also find out the winners through the Twitter account. Now, without further ado, we are ready to start our showcase. So again, we have 9 total teams, and team number 1 is the Trachea Tracker portable app. It is a Flask-based portable application to query PACS using DICOM Web that works even in a closed clinical network. And the presenter will be Dr. Sundar Kanya.
Yeah, can everyone hear me?
Yes.
You got it, you're live.
I see you nodding. And I would like to ask, Sai, do you have audio? Can you speak?
Yep. Yeah,
okay, so my co-presenter, Sai Natharayan, is also there, so we can begin. It is always good to begin with the presentation because you can be the first one to thank the organizers for the opportunity. And I would like to then use this opportunity and thank for all the opportunity to present this application that we developed only within the last 6 days. On the 16th of May, we did not even know yet that Hackathon exists. but last weekend we saw the newsletter and started to think about what could we do in such a short time. And we came with an idea up, and I would like to show that to you. The name is the Trachea Tracker web application. And before we begin, I would like to introduce myself. I am Dr. Konya, a radiologist, a neuroradiologist fellow, an interventional radiologist and AI fan. I have no academic training in programming, but I took part in many massive open Coursera courses that helped me to satisfy my curiosity and need for further education. And Sai, could you please introduce yourself?
Hello everyone, I'm Sai and I am a PhD student at the University of Pompeu Fabra in Barcelona. I'm doing an industrial PhD with 3D Shaper and Galgo Medical, which is a unit of Galgo SL. And I'm working on a project known as Disk for All. It's a European consortium-based project where we develop methods to understand and analyze the progression of intervertebral disc degeneration. And I started recently this March, and currently I'm working on 3D reconstruction from 2D X-rays and also working on texture-based modeling of the intervertebral discs.
Good. So we try to figure out what should we do, and there's a problem with the clinical radiologists and researchers who are working in a clinic due to the lack of the opportunities to get bulk data, image data, or clinical data, because the clinical networks are usually closed ecosystems. The users has no rights or really restricted rights, and the IT departments are not really competent in such a clinic. And it was a really hard time to get a DICOM node for myself due to license problems, and it is not flexible with the fixed AI title, could not use on every computer in the clinic. And we wanted to search for alternatives, and we tried, we get crossed on Cornerstone, which could have been used in the front end and the client side, but sadly our vendor in the clinic had the curse of course, so we could not access the data so as we wanted. So we searched further and we come upon with a solution where we could utilize a portable full-blown Python development environment. You can search up for the GitHub repo, and we used this WinPython environment to install every framework and a server that could help us to come over this course issue. And we use the Flask as a lightweight server, and we have experience in Python programming, and on the client side, the well-known frameworks, Bootstrap and jQuery Lodash libraries to develop. We wanted to show you an example use case, and not just the retrieval of images through this web application. And we chose this segmentation problem, which is the segmentation of the endotracheal tube and the airways, not the whole airway, but the first division of the windpipe. It's called bifurcation of the trachea, and it's an important task for every radiologist to look for this on a chest X-ray, because the position of the endotracheal tube must be set, and if it is too low or too high, it has to be repositioned. So that's a therapeutic problem. And we took part in a Kaggle challenge recently, where sadly my team could not participate as much as myself, I ended up annotating 5,000 X-rays for that with the tracheal bifurcation. But what ended up good that the winning solution could use this huge annotation dataset for the winning of this Kaggle competition, and we try to use this dataset to develop our tracheal bifurcation segmentation program.
Now coming on to the instance segmentation, so like when we compare the current state of the art instance segmentation methods to the previous years, one of the most famous solution is the mask RCNN method. So what happens in the mask RCNN method is that the algorithm first proposes a collection of regional proposals, and the algorithms are used to train the regional proposals into getting an accurate mask. So these regions of interest could be like vertebrae, or for example, in our case, we segmented the trachea. And in the next step, what the mask RCNN method does is to classify these segmentation masks and then perform the mask regression. So when coming to our first stage, we have the object and region proposals. And then in the second stage, we have the computation of segmentation mask and the class confidence, like how well the model is able to predict the bounding box, and then also the offsets. Further work on the mask RCNN methods were much focused on improving the feature pyramid network. Like it's a collection of convolutional batch normalization and activation layers which are collected over together, and then the features are compiled, and then the projection is made on the localization and the mask confidence. So what are the main drawbacks of these two methods is that though they have a high accuracy, but they have a low performance considering the real-time performance. So we need some model that does faster inference on the real time. And also the models are more dependent on the localization of features. So here's where we use the EOLAC model, which is known as you only look at the coefficients. So what it does is that this is a one stage of instance segmentation model. So when you consider an instance segmentation model, you usually have an object detection stage and also a segmentation stage. So in the first stage, what they does is that they propose a new network called as the ProtoNet, which accumulates a set of features over different intervals. Like here we have a 69 cross 69 image features over 2'6" channels, and then on top of that we perform the 3 cross 3 convolution, we get the same features, and then we perform the 1 cross 1 to get 138 cross 138, and then similarly we have the k categories of channels as the final features. In the step 2, the mask coefficients of these features are calculated, where here we have the class features, the box features, and also the mask features. So in the second stage, what usually happens is that we need to combine these two stages together and then perform a linear operation on the mask coefficients as well as the prototype masks. So the second stage is usually a matrix multiplication, and then a sigmoid function is operated on the output of the stage 2. And finally, you get the instance segmentation mask, for which there are 4 different types of losses. One is the mask loss, one is the class loss, and the other is the segmentation loss, and also is the bounding box loss, which regresses the bounding box so that the accuracy is even better.
Gentlemen, you have 1 minute.
Okay, and in this remaining minutes, I would like to demonstrate how the program works. I hope I can then here reload this page. That's is going to live query the SIIM Hackathon server, found 7 images on the server and started to inference them, and shows the inferenced image and the annotations on each image. It is pretty slow right now. It went a little bit faster this afternoon. I wanted to show you some examples that I just queried from the web. It shows really good results with the exact position of carina and the tracheal tube. Here shows also an overlapping 2 areas. We calculated the intersection over union value, and if it is more than 0.7, then we said that this is an anomalous, so anomality, and just would like to show you how it looks like when anomaly is detected. Restart here. Yeah, I just see a desktop notification, and I can open then the case in the background with a CLI comment, and that is good when the radiologist maybe doesn't have this application and on the desktop running, but
you are
it's
at
running
time
somewhere on the background. So basically, we wanted to prove that it's possible to use a portable application to get to the pictures and also to integrate ML scripts in the pipeline, and it is also within 5 days possible. So thank you for your time and
thank you, team number one.
questions.
Judges?
Can I ask a question?
Yes, please. Judges, please go ahead.
Yeah, assuming that you use DICOM Web to retrieve the images, I was wondering how you would, whether you have already a solution to store the annotations, or whether you're thinking about how to store the annotations, whether you want to have that information sent back to the PACS, or what are your thoughts on that?
The intention is to make a flagging system. So
Okay.
like a prioritizing of the reporting of the images. If the system detects an anomaly, a low position of the endotracheal tube, that image has to be reported pretty fast, because it's a therapeutic decision that has to be made whether this endotracheal tube should pull back or reposition. And that's also that's the main intention, to have a flagging and prioritizing system to show which image needs your immediate attention.
So it's AI triage. Okay, thank you.
Yeah.
Thank you.
Other questions for team number one?
I was kind of in the same vein, I guess. Dr. Konya, how would you see the workflow for this going? So would the idea be that these patients would be scheduled for periodic, position check X-rays, and you would somehow detect which ones were for that purpose, and then, flag those for the radiologist? Or
so we have in our clinic, in our system, we have the bedside images named always with the same words, and that's the filter for these images that could possibly contain endotracheal tubes. None other, the not bedside images are not usually, so they do not contain, the patients are not on the intensive care unit, so they don't have an endotracheal tube. So this is a niche application only to detect this narrow pathology. So that was the filter. But maybe later we could add a classification script too that helps us to identify the chest X-rays if the series description is not enough.
Thank you. That was team number one, the trachea tracker portable application. Next, we have team number two, case tracking project. It's a software able to capture a screenshot of a radiology image and metadata such as modality and body part, all in a user-friendly interface for case tracking. The presenter is Vadim Kurtzukov. And Vadim, whenever you're ready, please go ahead.
So this is Sina, another person in the team. I'm going to give the introduction, and Vadim is going to continue with the demo of the software. So yeah, hello everyone. I'm Sina, and I'm a radiology resident in Pittsburgh. This problem that we are trying to solve in this hackathon is about case logging and keeping track of cases. As you know, all of the radiologists are dealing with this problem, and it's a really time-consuming process. There is need for case logging in education credentialing, possibly billing, and we are spending a lot of time in doing this during our practice. In addition, we also save lots of images for our presentations, case conferences, or just taking pictures for keeping them or sharing them with our colleagues. We tried to find a solution for these two processes by designing a software which universally can keep track of cases, easily log, keep track, and also take screenshots and save the images in an appropriate way for future reference in a safe way. Vadim is going to continue and show us the demo of this software.
Can you hear me?
Yes.
Yes.
Okay, so the prototype of this solution, I chose to make it simple, local, remove extraneous complexity. And to achieve that, I just used Excel as a data storage and just a designated folder for archive of the cases. For user interface, based on what I've heard, I chose to use kind of a clicking and tagging as opposed to typing, minimizing the typing and input, and make it as fast and kind of easy as possible to quickly write down some notes and save this for later. There is a need to capture a few things, possibly screenshots, and everything is going to be stored locally. So no sharing, no uploads, none of the security implications. It's a mini, my personal favorites archive, basically. Based on the 3 iterations that happened in the past 2 days, 3 different versions were built and reviewed and enhanced. The final version included the ability to have just localization of like which hospital are you currently working at, because some people go to multiple places, multiple sites, and just recording a case doesn't necessarily give you an idea where you saw it if you come back to it later. So there's just a basic need of to know which system, which health system, and which PACS system you saw that case at, and then the ability to anonymize. For some cases, you actually don't want to store PHI information, so a system, the software will allow for this stripped down storage. So the prototype, these are the screenshots, would be a tiny little app, simple save to log button. The user interface, as I said, has tag style of like tagging, which modality, which study, type in the protocol description, male, female stuff, MRN accession information, quick type note of why is this interesting, a few checkboxes on the bottom that are allowed or allow you to track and enter, is this good for local conference, is this for national or society level conference, is this for a paper you're writing, manuscript stuff. And then you don't see there's a dollar billable amount thing, but in a special case when this could be potentially used at certain sites where radiologist reads and then has to keep a log and maybe write down the amount. I mean, I saw one of the templates shared that contained that field. So it's an optional feature. None of the fields are required. All are simple data points with a possibility of multi-tagging. So if a study for some reason contains head and neck and spine, you can actually tag all 3. They're going to be aggregated all together. So if you search your Excel repository of data, you will find the case regardless of which keyword you're going to search for. Then there's ability to grab a snapshot, and I had to simulate my. I don't have any reading software, so I can't see X-rays. Wasn't going to, but what I did, I just made a fake reading workstation screen that I used, and the picture you see of the cup is actually an entry in the Cleveland Clinic Imaging Institute art contest from prior years from one of my colleagues, and I thought it was really cool. So the software allows you to select the region to grab, and you can capture several of these. So you have data plus the images all there, and then you just hit save. So when the data is actually recorded in the backend in Excel, this is what it looks like. The log ID is a combination of date and timestamp, so serves as a universal or unique identifier, as well as the date timestamp. The green fields are hospital, study, body parts, protocols. Red fields, or highlighted in dark orange, are the patient info. POI is the note that why is this case here? Why is it interesting? The three flags are local conference, society, or manuscripts, and then dollar amounts and the case folder. The case folder column actually is a clickable hyperlink. So when you click on it, as you can see, on the bottom, there's a finger thing. When you click on it, it opens up this image folder with all the images that you saved as part of that entry. So it's like a skeleton style, notepad thing, story, quick notes. I don't know. All right, so now I guess it's the time to do a demo. Switching to, you can still see my screen, right?
Yes.
Okay, so here's my little save to my log application. I'll move it like here.
You have 2 minutes.
You have ability to select the location. This is the viewer. In the first iteration, the viewer was defined and the system automatically grabbed the screen, but it was just extraneous info, which was part of it, which was not really needed. So in the third iteration, if you start the note and you define some parameters, I'm not going to go into too much detail here. I want to say I want to grab this. This looks good. I'm going to add this, and the system said okay. And I want to maybe grab this. So okay, that is fine. I can say that, but then I actually don't need that one. So I'll keep this one, and I'm going to write this out. And of course, it's going to probably fail on me, but this is due to the last minute enhancements. The resulting thing works. And here's the archive entry, or here's my local archive. So let me just make sure it is. Okay. It's not responding now. Oh, breakpoints. Okay, never mind. So the archive is right here. Here's my last entry. Here's what I just typed in. And if I click on that, it opens the archive folder. And there's some test images that I've done before. It just sequentially creates screenshot 1, 2, and 3 once it's processing that.
You're at 10 minutes. That's time.
Okay. So future enhancements, encryption, the dropdown of protocols, annotations for the captured images, and customizing actual Excel file with column order, and maybe saving that as a profile. That's it. Any questions?
Thank you, Vadim. That was Group number 2, case tracking project. Judges, questions?
Yes, thank you very much, My Case Log, for the great presentation. If you would like to develop further the My Case Log, what are the features that you could imagine to make My Case Log have a larger impact beyond a personal case log or a personal local case log?
There are some things that, based on what Sina and Pedro was telling me, there might be some usefulness for the residency, for tracking education, but I have to let them speak to why we're doing this.
I can talk a little bit. So I think that the ideal application would work anywhere in any computer, and it would be linked to your credentials, like something that you could log in. It could be a web application or a software like thick client, and you would be able to store all those metadata and large volumes of like large sizes of images, including DICOM ideally. So if we could do that, and if it were HIPAA compliant and easy to use, just like I can go somewhere else and use my Facebook anywhere else, and it does have my personal identifiers there. If I could use that, if I could have the same safety and freedom to use that application anywhere in the world, I could have a lifelong record of cases. Ideally, it would be like a Google Drive, essentially, that you can have folders within it, and you can have that portable, all in the cloud.
I also wanted to add one additional use is that it can be shared between users, and like we can send cases to our colleague in another health system and hospital, completely independent, with like desired screenshots. And one additional thing that we want to do is customizing the cropping of the images. So now we basically did like a screenshot of the whole screen, but we can manipulate the cropping, add arrows, and annotate the images and save them, and multiple images.
Just a real quick comment. I think one of the other feature enhancements that would be really nice is to pre-populate or post-populate some of the clinical metadata by doing like either a fire call or a DICOM web call based on the accession or something along those lines, to try to reduce the amount of potential human error introduced and reduce the barrier to logging a case by utilizing some of those APIs.
Thank you, judges, and thank you for team number 2, case tracking project. Next, we have team number 3. ROSA stands for Radiology On-Screen Assistant from the Cleveland Clinic team. It is an unobtrusive on-screen radiologist assistant for providing contextual integration between client apps running on a radiologist workstation. And Lindsay, as soon as you're ready, take it away.
You can hear me, right?
Yes.
Okay. My name is Lindsay Marrero. Good afternoon, evening, morning, wherever you happen to be today. I am representing Team Cleveland Clinic, and our hackathon project this year is what we have dubbed the Radiology On-Screen Assistant, or ROSA for short. Here we go. Okay. Our team this year was a collaboration of different people from different backgrounds. We have our imaging data science team from the Cleveland Clinic. We also have our medical physics development team. And we have 2 students from John Carroll University, and they are computer science grads. So it was nice to be able to.
Lindsay? As a reminder, if you're looking to present your screen, you are not sharing.
Oh, thank you. One moment. Screen share. Nope. Okay. Better?
Yes.
Awesome. Okay. You didn't miss much. This was only the second slide. All right. So our challenge this year that we wanted to develop a solution for was, we all know that radiologists use multiple different applications with multiple different vendors all at once. There's no consistent client integration. And you know, in an ideal world, we would have, you know, our RIS talking to dictation, PACS talking to EMR, EMR talking back to RIS, whatnot. As you can see, it gets kind of spaghetti-ish down here. So we really need, and there are standard integrations now that do rely on HL7 messages. They're very proprietary. Because of those messages, you could potentially have network latency, and you know, they're custom built for each integration. So there really is a need for a vendor agnostic integration solution. And big picture, you know, from a radiologist standpoint, we need this contextual awareness. So, you know, a radiologist really just wants to know that program A is talking to program B. Program A, we want to know what's happening in program B. So our idea for a solution, and special thanks and shout out to Dr. Chen and Dr. Poster from the Cleveland Clinic for helping us with this idea and providing some inspiration for this, is ROSA. And ROSA stands for Radiology On-Screen Assistant. It's basically, the idea behind it was we wanted it to be an unobtrusive assistant that is present but not distracting. It will automatically detect events that are happening on screen, whether data is placed on a clipboard, or maybe there's a value within a UI element in your PACS, RIS, dictation, etc. system. We needed to have contextually suggested actions, such as, you know, hey, I've detected a patient ID. Do you want to view priors? Do you want to open up the patient in an EMR? That sort of, those sort of suggested actions. And we need to use quick access to actions via the FHIR API calls. So now I'm going to hand it over to one of our students, Jess Marola, to walk through a demo.
Thanks, Lindsay. So for this example, we want you to imagine that you're a radiologist and you're working on dictating a report for a patient named Joe SIIM. So Lindsay has that example pulled up right now. And as you're working on this, you might find yourself wishing that you had quick and easy access to more of Joe's information. And this is where Rosa is going to come in. So this whole time, Rosa has been running quietly in the background, and you could see the symbol, the little widget in the corner at the bottom of the screen. And so now if we highlight the text, so highlight the patient ID and add that to the clipboard, Rosa is going to be notified, and you can see that through the highlight. And so once we have that added to the clipboard, we can open up Rosa if we want. And you can see that we have two features that are currently implemented. So the first one we're going to take a look at is the load patient studies feature. So we'll pop that open. And just from adding that patient ID, we can see the patient's information along with a list of studies pertaining to that patient. So you can view the information, or you can select a specific study and hit the button, and that's going to take us to a PACS viewer. And now we can view the images pertaining to that specific patient. And we have a second feature as well that I mentioned. And in this case, it's Google and whatever, you can Google whatever's on your clipboard. And so that'll function pretty much as it sounds. But what our plans would be for that is, rather than being able to Google something, you would be able to take whatever's saved to your clipboard in the future, and instead of Googling, you would be able to search that clipboard piece within our internally developed radiology search engine. So obviously that wasn't quite available for the scope of this current hackathon, but it's one of our future ideas, and I'm going to pass it on to my fellow student, Chase, and he can talk a bit more about those next steps as well.
Hey, Jess. Wait a moment. So our next steps for Rosa would include the following. You can go to the next slide, Lindsay. Thank you. We would want to include a way to look up by study ID, as well as include user-driven application configuration. So this would allow users to configure Rosa for EMR, PACS, and RIS. We would also want to give the ability to open patient information in EMR, RIS, or dictation, We would also want to add a capabilities to open my case log for studies being reviewed. And this was the previous hackathon project that you just saw, actually. We would also want to include a report checker, which would specifically look at subspecialty specific quality checks against the current report open. And there are many other things that we could look at. This is just the beginning for ROSA. We can add many other things, even through something like a custom script. I will now pass this to AJ, who will go over Sonar Cube for our project.
So as part of the hackathon, we had the opportunity to try out Sonar Cube. Sonar Cube is a code review tool that helps identify bugs and other issues with your source code. So after you install, configure, and run the Sonar scanner, you can then view the results in the Sonar Cube website. So here on the left, we have a view of our dashboard after we ran a scan. You can see it's got one security issue, 109 code smells, which is code that is confusing or hard to support, and 7 hours and 40 minutes of debt, which is the estimated time it would take to correct all the issues that it found. It also keeps a history of each time you rescan or refresh the results, which is on the right there. So this graph is showing our issues increasing as each time we refreshed. Ideally, that would go down. You can also drill down into specific issue details. Here is a code smell issue for cognitive complexity. It shows you the code that it identified as problem code. It highlights areas that it thinks is confusing and should be modified to make supporting the code easier. Due to time constraints, we didn't follow up with any of our reported issues for this project, but we can see this as being a helpful tool within the software development lifecycle.
So we did decide to open source our code this year. It is in GitHub, and we are just waiting on administration approval from the Cleveland Clinic just to make sure that we're good to go. But it should be with, we're hoping that it will be out there. And we do have a reference to the report checking software that we referenced prior. And then our hackathon experience, we were successful in proving that this application can exist to tackle a solution we tackled the solution that's plaguing many radiologists out there. This was a virtual experience, obviously, this year, and everybody had their own modular components that we tied together at the end. That worked out really well for it being virtual. We worked with students this year and multidisciplinary teams, which was great. Shout out to our code heroes, because there were quite a few times where we were like, oh, how does that work in Fire? What kind of call do we need? So that was really helpful. And Sonar Cube was a great add this year. It was a great opportunity to use that this year. With that, we can take questions.
Thank you. Judges?
Have a question?
Sure.
Yeah, let's say, by the way, I like it, but let's say we have a name John Smith. You highlight John Smith, and I would imagine that there are probably maybe, if you take the Cleveland database, 100,000 matches. How do you think you're going to filter out multiple responses?
So that's a great question. Right now, we have it set up with patient ID, which is pretty, that is the unique patient identifier. And as part of our next steps, we were thinking about using a study ID as well, but due to time constraints, that was an issue. I don't think we talked much about using a patient name, because yeah, that would cause quite a bit of a problem if you've got multiple John Smiths. But ideally, I mean, it would be nice to come up with a pop-up, maybe saying, hey, did you need this person or this person? And then maybe validate with those two patient identifiers, right? So patient ID and patient date of birth or something like that, so that we can properly identify the patient. I think that would be a really nice add.
Thank you.
Mm-hmm.
You mentioned, oh, go ahead.
Have you thought about a more automated way of capturing the context rather than having to use the clipboard?
Oh, okay. Oh, I'm sorry. Was that the question?
Yes.
Well, and actually, I'll supplement the question because I was thinking along the same lines. You mentioned using the Fire APIs. Specifically, did you look at Firecast? Because this would seem to be really well aligned with, to Chris's point, to have the program help queue up some of the context. I think the clipboard is handy for additional context, but
Okay. Yeah, I mean, I'm not familiar with Firecast. I'm not sure if any of my other team members might be. But so you're saying that maybe we could queue up some different identifiers?
Firecast was intended to be sort of a context synchronization thing so that it's a bulletin board. And when one app says, well, all right, we're opening patient X, it throws up the current patient ID, the current accession number, and any other apps that are saying, hey, if we've moved on, give us a ping, and they can go look and say, oh, we're on this patient now. And so it's a way to have sort of background. To Chris's point, you could automatically be syncing up on the patient. Now, some of the other things, if you have a particular diagnosis, that would be a little more complex.
Yeah, I mean, that sounds like it would lend itself really well to, yeah, what we were looking into. Yeah, that would be really cool because, yeah, it is kind of cumbersome right now. Right now, it's relying on it being in the clipboard, which isn't ideal, right? You don't want to have to like select somebody in your clipboard or select somebody in your report and add it to your clipboard. So, yeah, definitely open to other solutions with that.
Yeah, Firecast is really the modern way of doing CCAL, which is the old way of doing context exchanges. So you might want to look at those.
Okay.
Thank you,
Great.
judges. And
Thank
so
you.
we do have to move on to the next presentation. Some of the conversation continue in the chat for some of the presented projects as well. So I encourage everyone to check in the chat if you want to continue the discussion. But we do have to move on to, so sorry, that was team number 3, Rosa, Radiology On-Screen Assistant from the Cleveland Clinic team. Next, we have team number 4. I think it's pronounced PokeRad, Gamify Radiology. It is a proof of concept resident training system with gamification elements. Users accrue experience points and level up based on performance, which in turn unlock other training modules. Team number 4, PokeRad, when you're ready, take it away.
Can you see my screen and hear me well?
Yes.
All right, so this is PokeRad. I'm just representing this large group of amazing people. I'm presenting for the first time. I'm a radiology resident here at Boston University. So just a little bit of background. So there's a problem. Each radiology resident throughout their residency will see a different set of cases. So for example, it's the luck of the draw. One resident will see 5 cases of cardiac amyloid, for example. The other will see, will become very familiar with lung rads. The other will have, will witness many cases of severe trauma, but the other resident will not. So how could we help solve this problem? How can we ensure that all residents go through a similar set of cases throughout residency? So we could implement training sets for training modules for specific skills. For example, a training set that a radiology would do that would have them become trained in lung rads or in bi-rads, or like a call prep sort of training module. And you can use AI techniques and gamification to make it more engaging. So what is gamification? Gamification is the application of elements of video games especially, to make something more engaging and fun. So these are examples of game design elements that we apply to things to make them more engaging. You can have a point system, you can have badges, you can have leaderboards, performance graphs, meaningful stories, avatars, teammates. So what is the evolution of a radiology resident? So all the kids from the 90s on this call know these pocket monsters. So you start as with a Charmander, and they evolve, and then they evolve again. So what level do they evolve? And I know that you know that. In your memory, you probably already know what level they evolve. Level 16 and level 36. So a resident is kind of like a Pokemon in that sense, right? So your objective is to become a Charizard as an R4, a resident of the fourth year residents. So at that point, you should be able to work independently, participate in tumor board, but maybe as an R2 or R3 here in the middle, you should be able to take call and be very effective on call. So there is a sort of a pre-specified level of evolution, even for residents. So we had an idea that was kind of like this. If you had sets of modules, one set of module for each skill that you want to evaluate or train on. So for example, lung rads, you could have 4 sets of modules. So these squares are sets, are modules. So you would have one set of module for lung rads, and at the end you will get a trophy, for example. Now, for example, cancer staging. Maybe in order to start your cancer staging set, a module set, you would have to have gone through the lymph node training set of modules, and then this will unlock the cancer staging because it should be really good at seeing the lymph nodes that are abnormal and giving them the right name. So one set of module will have many modules, and each module is kind of like a dungeon and could give a maximum number of experience points, XPs. And each module is a little bit difficult than the prior module. And each of those modules can reward up to a predetermined number of points. And it will cover a certain level of difficulty and tell you how much you got right. One example that we could do, one way we could apply this is with image segmentation and annotation. So for example, if images are annotated with the ground truth, like these ones, maybe the radiologist is the ground truth and then the resident is trying to find the finding. And this particular resident got 60% correct. Maybe 60% will reflect 6 XPs out of 10. And then, throughout the entire dungeon, maybe there's 100 cases, so a maximum of 1,000, but the resident got 850 XPs, right? So the XPs will go to this resident's total pool of XP, and they will climb up the ladder until they go up in level at multiple points. So let's say this is a resident. If he's a level 6, maybe one day he'll be a level 7 like that, right? And you will have some visual cue saying, hey, you went up a level, great job, keep at it, right? And then maybe you could apply leaderboards. So, this resident here is in first place and got a trophy, got a crown. And then there's someone who's in second place, third place. And you could have rewards, trophies, badges, specialty related badges or streaks and trophies. So why to do all that? We'll go through all this, right? Maybe you'd have something like this. You need to be a level 30 to be okay to do call, for example, because they would know that you're very effective at that. Maybe you would be level 45 to be able to present a tumor board. Maybe a level 5 to lead a clinical project. And the other advantage of this dungeon system is that you would ensure a similar pool of cases for those training modules for all residents, right? So this is an example of a TB detection. So these TB images were available to us, and there is a ground truth annotation. And then we annotate these images on this open source software, VIA. In this example, there's this marking that is let's say 60% correct. The second step would be to calculate something such as a DICE coefficient score from 0 to 1, right? So 0, the person is completely off, and 1 is 100% exact. Like you see in this drawing here, DICE of 1 is completely correct. The third step would be to assign an XP score per DICE score. So let's say multiply by 10, 0.8 DICE score would give 8 experience points. And then step 4 would be to sum the XP for each image annotated to calculate the XP for the entire dungeon. And then you could have a leaderboard and leveling. So this is what we did so far, right? In 48 hours, and what Dr. Les Folio has worked recently as well. There is this single one-stop shop for everything related to annotation, and you have annotation training, publicly available images, how to download the VIA open source software, how to upload the JSON for instant score. And then we have used these two data sets so far, 27 patients of COVID-19, 68 of TB. And then there are many of us who already went through that very quick training and were successfully, we were able to successfully annotate those images. The time range depends on your training. We had students do it as well. And we had, fourth year residents. And this was the first leaderboard that we did. this is, so to speak, version 1.0. So this one was based on kappa statistics, and we were able to just rank the imagers, annotators based off of the kappa statistics. But now in version 2.0, thanks to our wonderful code heroes, we're able to do something a little bit better. So this one is for the TB annotations, and João, one of our code heroes, was able to create this little website that you can just drag and drop your JSON file and submit, and the leaderboard gets populated automatically there. So this is us having our first demo. On your left side, you see the happiness of a working demo during conference. And then on the right, you see the little thing being populated. So I don't know why Marcelo is not that happy because he is first place on the leaderboard, but maybe it's just because he knows it's just 2 people on the leaderboard so far. So he's a realistic guy. So the demo we have is this little video in which Marcelo is inputting his name. It was Eduardo's score, so he's typing Eduardo's name. And then he has the JSON file that he got from those annotations. He's just going to drag it into the drag and drop field. And then I guess he gets confused with the mouse for 1 second and then submits, right? So as he submits, you see Marcelo is there and Eduardo is there as well, okay? So for the future, now we want to streamline the existing methods and codes that we've got and have some real-time leaderboard updates, build up on Siva's work as well, who works with Dr. Les Folio on these things. We can automate this process, apply the same rationale to other kinds of tasks like reporting or some sort of online form. You can click through things and choose the Lung-RADS category, for example, use other modalities, something that you can scroll, a nicer user interface, an interface with a profile, with authentication. And we think that the potential of something like that is to revolutionize the radiology training and evaluation. Maybe something like this could replace an OSCE or multiple choice questions because you have a track record of what kinds of modules that this resident did, right? It could also replace our boards, maybe an oral boards 2.0, maybe identify students with talents, and also create crowdsourced annotations. For example, this is Les Folio's work with crowdsourcing annotation and how he can create heat map plots showing where these annotations are
10 minutes.
so that you have, this is essentially it. So a shout out to everybody who helped me, and thank you so much to allow me to participate in this hackathon. Really appreciate it.
Thank you. Judges?
Thank you very much. Great presentation. How would you assess the impact of your application on medical education and professional development?
So I think that a student or resident trainee would be able to have a very standardized training if there was a training module that people could do that would ensure the skill set that you need at the end of it. So this would be very significant for training of students and radiology residents.
And who would be your preferred partner for this application to have a long-lasting and significant impact on radiology education in the US first and worldwide?
In terms of company or?
It could be company or academia, institutions.
I can definitely see RSNA. I can definitely see RSNA building something that is like this with profiles just like LinkedIn and Facebook. People have their profile, but something professional and related to radiology. And, you know, just everybody has to go through the boards exam as well. So maybe ABR. ACR has modules that they have available for people. So it will be interesting for ACR as well. So I see one of the 3 societies to, you know, being interested in this.
Thank you.
Thank you. That was team number 4, PokeRad, Gamify Radiology. Next, we have team number 5, that is team 1Qubit. The project is to create a low-cost AI radiology triage system that physically requires only a smartphone, a Wi-Fi router, a Raspberry Pi 4. based on previous AI work for chest radiograph from the same team. And team 1Qubit, as soon as you're ready, take it away.
Hi, everyone. My name is Anush Sharvan. You can call me Anush. I'm calling you from beautiful Vancouver today. Along with me, I have my team members. So let me just share my screen. Okay. So, I mean, we're calling the project sort of Pi. It's a bit of a little visual pun. If you like visual puns, we got more of those coming up. So the team includes Seva Radchenko, Ovid Durbalau, Savio Montero, and myself. It's worth noting that Ovid and Savio have just joined the company like less than a month ago, and they're already participating in this hackathon. So really new team here. And we are essentially, all of us are software developers, and we work in the healthcare division at 1Qubit. We take the machine learning models that are developed by our data science team, and then we build applications and the necessary infrastructure required to deploy them in different scenarios. So a bit of background, we didn't develop this machine learning model over the last 48 hours. We are using something that we have before. It's an in-house deep learning model that identifies lung abnormalities in chest X-rays. It's very similar to that project team 1, I guess, with the trachea abnormality detection. But we're focusing on the chest abnormality. We're calling it X-ray, and it has been certified as a Class 3 medical device by Health Canada. So in the production setting, the model is deployed as a service-based application that behaves as a DICOM application entity. So it can accept C-stores or C-moves, and it's an SCP. And internally, we have also tried deploying the model behind like an API on the cloud. We use Azure. So kind of this is a sketch of our production deployment model of X-ray, where you have a PAX that sends a C-store to a DICOM listener. That is the application entity I mentioned. This creates the job and the job queue and also stores the image to disk. And then we have one or multiple workers that could then crunch through those images and send the result back, C-store back to the PAX. I didn't include that in the diagram here. For the cloud API model, it's a very similar thing. Instead of a PAX, you just have a REST client that interacts with REST using get and post commands with an API server. We essentially have 2 endpoints there, one for creating the task and one for the data. Because the data takes storage and needs to be stored somewhere. For a cloud model, when you first post your image to the data endpoint, that gets stored to the blob storage, and then you create a task for referencing the ID that you got when you posted the data. And then once the task is submitted to the job queue here, then you have, again, workers on the cloud that could then process the job. Now, the cloud platform that we have is just internal for internal use. We can't, as has been mentioned before, clinical environments are usually closed ecosystems. So for production deployments, this is deployed on premises on a VM. So it would be like a Red Hat VM or something like that. So the problem, what is the main problem that we're trying to solve, right? So if we can run the chest X-ray ML model on an existing API server on the cloud, can we also run it on a low-cost, low-powered edge device too? And then the follow-up is, can we use a mobile phone to take a picture of a chest X-ray, send it to the edge device for analysis, and then receive a response? I mean, the main use case for here is really kind of for humanitarian purposes and environments where there's low amounts of financial or technical resources, right? So this is kind of the sort of rough model of what we wanted to achieve during this hackathon. This mobile app here that takes a picture of a chest X-ray, and then it's able to get and post to either the Cloud Inference API or the component that we built here. So this Raspberry Pi, the Wi-Fi router is able to communicate with the phone and accept the jobs. So there are a couple of main components of the software part. So we have the chest X-ray ML model. It's based on an Onyx runtime. The input is an image of a chest X-ray in JPEG form, and then the output is a prediction, whether there's abnormality or the image is normal, a confidence score as a percentage, and a sort of resulting image. In our demo, we're going to be primarily showing you the resulting image. That's the heat map overlaid over the original chest X-ray. The API server, it also runs on the Raspberry Pi, listens on port 8080, implements essentially the same /data/tasks endpoints as our main cloud API, just for consistency, but it's simplified, so we're not doing all the same level of details there. And then it calls the Onyx model for the actual inference analysis. And then finally, the mobile app that captures the CXR, sends it to some API, whether it's the Raspberry Pi or the cloud, and then displays the result from the API server. So this is the hardware that we end up going with. I took a screenshot of actually purchasing this. We're really stretching the definition of like low cost, low power, I guess in this case. It's not a $30 cheap a Raspberry Pi. It is probably the top of the line currently at 130 Canadian dollars. And we've got 8 gigabytes of RAM in there. And in terms of storage, it's a 64 gigabyte SD card with Ubuntu desktop and ARM64. We picked 8 gigabytes because our model, it has a minimum of 8 gigabytes of RAM memory requirements. And then as part of the process, we did a quick sprint planning. We broke down the tasks and assigned it to kind of the 3 different people here. Savio handled the web app, Obid did the RESTful API, and then Seva ported the X-ray Onyx model onto the Raspberry Pi, and I sort of did the infrastructure work and some of the other tasks. For the Onyx model, the challenging part was porting everything to ARM64. We had to compile some of our dependencies for ARM64 as well, and then we had to hack out parts of the model that just could not be converted over to the architecture, or we had to hack it out, like remove some of the things that were too heavy in terms of resources. API server, I won't go into too much detail here. It's basically, you can do go post and get against both these endpoints, and you're going to get the result back. And then the mobile app is essentially a hybrid app where we have the web GUI as predominantly the interface, and then we use a native bridge to access the phone's camera. Okay. Now I think we're ready to do a quick demo, and let me just we are going to do this live. I'm going to change my camera to this. So what you see here is this is the actual Raspberry Pi in the enclosure, and it's hard to install Zoom, so I can't really share the screen on the Raspberry Pi, but hopefully you can see some of this. And let me just stop sharing here. Before I go. And share my screen once again. So are you able to see this shared screen right now?
Yes.
All right. So I think we're almost ready.
You have 2 minutes.
Yeah. Can you capture the X-ray? Yeah. And then we're going to do this. All right. Starting the timer. Just to have an idea of. Okay. So we started uploading at around 6 seconds. We seeing some activity over here. Okay. Here you see an image. This is the original image that we just received. I'll actually open it. Can you open that? Open. One more time. Oh, there it is. Yep. So this is the image that we've taken with the photo. It's on the Raspberry Pi, and right now it's still currently processing. If you could close this now. Yeah, so the mobile app has submitted the job, and as you can see here, it's just querying. It's just polling for the status of that task. In this case, it just says the task is submitted. You have the data ID here, which is the same ID as the image name on the Raspberry Pi. Task ID, and then the task type, so it's a chest X-ray inference. So I mentioned that in order to get this to work, we had to do some trade-offs, right? Like we for the production model, we have some extra filtering that we do that are also Onyx models. We have one that detects whether it's an X-ray image. Like if the image that was submitted is an X-ray at all, or is like an image of a chair. And then another model that detects the view position, so whether it's AP, PA, or LAT. And so we're not doing all of that just to make sure that we have enough resources on the Raspberry Pi. Another model that we use is the segmentation model, which essentially creates a nicer map. Right. So we're just, if we could get this result back soon, just to give you an idea of what it looks like. Yeah, so it does take a while, especially again on the Raspberry Pi. Typically, oh, there it is. So if you can scroll down, you see now the highlight of the heat map, and it's growing and changes, and you can see on top it says confidence at whatever %, right? So we're outputting a GIF of multiple JPEGs with the heat map, and at the lower confidence percentage, the heat map is larger, and then at higher confidence, the heat map is more narrow. And just to give you, yes, that took about, let's say less than 2 minutes, around 2 minutes or so. And this is the same image on Osiris that we run with the production model. We have a little bit more control. You can see that the heat map is actually within the lung boundary. So that's kind of the difference that we really have of this kind of production model versus the Raspberry Pi. And yeah, if we had a chance to improve it, we'll try to parallelize as much as we can to get some more resources out. And I was thinking we could probably pair up with the previous team, the Polkarad. We can probably build an arcade machine or something that could then just like train all the other radiology students and stuff like that. So some ideas for future. All right.
Thank you. Sorry, was that your presentation?
Yes, that is. Let me just change the camera back to.
Thank you. We have time for one question.
Yep. Thank you very much for your time.
So this isn't a question, but I just want to say from my perspective as a pure non-medical patient advocate, I can just see the early symphonic sounds of all of this getting out from behind the walls of radiology and into the hands of the subset of patients who want to understand all this and learn from it. It's like, please give us, and Polkarad also, give us a way to get in and start learning.
Yeah, it definitely wouldn't replace a true radiologist, but for places that have nothing, absolutely nothing, it might be an actual something useful, right?
Do we have time for a quick question?
We are over time at this at this point. Is it okay to do it in chat or maybe reach out separately? Yeah. Thank you. So that was team number 5, team 1Qubit. Next, we have team number 6, Mastermind from Marquette University. And this is an application which pulls JSON reports from the FHIR server, extract key information, and then send back in a condition report. Mastermind, as soon as you're ready, please take it away.
Thank you. Okay, well, we're bringing up our screen here. So this year, we were actually back on campus today, yay. We are going to have 2 students present. They both just finished their junior year in undergraduate. On Tuesday of this week, they did not know what a radiology image was and had never heard of FHIR. So it's been a pretty interesting week. So first up, we're going to have Juliana, and then once we get to some of the other sections, we're going to have Tyrell. And on that note, I will let you take it away.
Great, thank you. All right, so first I'm just going to start with a little user narrative about the patient. So a 69-year-old male with a 60-pack year smoking history wakes up one morning with slurred speech, dizziness, and numbness in his right arm. His wife calls 911 and he is taken to the ED by ambulance. The ED physician immediately orders a CT/CTA imaging study. The imaging study is completed. However, this is a small rural hospital's ED and inpatient services are abnormally busy. This study is sent over a secure VPN to a faraway academic hospital to be interpreted by a neuroradiology specialist. So this is just a little background information. So now we're going to talk about the app Mastermind. So we get this new image study, and this is a what is it? The state diagram of stroke. The stroke status. So first, it's an unknown status, and then an AI stroke detection algorithm looks at this image, and it creates a fire observation, and the status is a draft. And it determines that there is a possible stroke. However, confirmation is needed from a radiologist, and then the radiologist will review the images and make the status final and say, yep, there is a confirmed stroke if there is. And then on the right hand side here, we have the stroke team notification, which is, you can see the yellow possible stroke. This is what will be sent to our app Mastermind, the user interface. And then has the bed location of the patient. And what we intended for it to do is when you click the patient name, it would show the DICOM image to give the physicians or the stroke team a little bit of an idea of what is to come. And now we're going to kind of put this all together and an overall system architecture of our Mastermind app. So first we have the diagnostic report is in the SIIM Fire server, and this is the back end of our Mastermind app. So we query for observations and reports. We parse the JSON file, and we look for any important information about this patient. We're looking for this code I-3063, and then we're going to create a condition and a communication to the stroke team, and we're going to put this on the SIIM Fire server. This is what our app, we would like our app to do. Once it is on the SIIM Fire server, it allows our Mastermind user interface to take that and to update this over here, our stroke team notification with yellow or red or white, just meaning, you know, unknown currently. And another aspect that we plan to implement too is the report sent using the SIIM Sol server. So now just a little bit about the Python code. So we wanted to use Python to do this. We are importing the JSON library in order to read the report that we got from Smart Reporting. And we wanted to create a program that looks for important information that we need to send to the stroke team. So the ICD code, the patient information. And then once the code is found, we want to create a communication request and a condition resource to be posted back in the Fire server. So that's kind of what we want our Python code to do here. And then I'm going to give it over to Tyrell to talk about how we use Sonar Cube with our code.
Can you hear me? I just can't destroy my video for some reason, so I'm just gonna explain like this.
We can hear you.
Yeah, I ran the Python code for the Sonar Cube server, and then like as you can see, these were the results of the tests that we got, and then we got A's for all of them.
And this was also our first time using Sonar Cube, so it was very new to Tyrell and I.
Yeah. So in the end, we couldn't implement Sol because we didn't finish like debugging and like making it. But we plan on using the Sol API for like logging what happens with the medical professionals, and also it should help the process engineers to understand what is happening with the timing of everything that has happened with the logging and then of the patients and of the doctors. And the reason why we have this is to measure the efficiency of each step that, I guess, for example, the radiologists do when they try to diagnose their reports.
Perfect, thank you. So now we're going to kind of go over additional use cases. So this primary care physician notification, as you can probably see from this slide, this whole notification center that our app is doing, you know, we're sending a lot of different reports, and we feel like it would be very easy to implement some type of physician notification if needed. So ASCII text reports, they use NLP to identify findings, and this is given to us from within health, and it's intended to create a FHIR communication request to an ordering physician. So this is another way we can just extend upon our Mastermind app. And this is not just the only use case. I think our team feels that this can be implemented in so many other ways, not just within radiology, but within other aspects of the medical field. So what's next for us? So as you can see, we didn't get as far as we wanted to with our code. We had a few issues come up, but I personally learned a lot. And I think I really enjoyed this project enough that I would hope to take it and use it for a concept for a senior design project this year, as I'm going into my senior year. And I think we can really work with physicians and hospitals and of course radiologists about what it is they want to see with this Mastermind app, and really make it for the physicians. I feel like a lot of times as engineers, we make things for engineers, and that can be a little bit tricky sometimes. We want to make sure it's very user friendly. And our Mastermind app is also open source and can be found with this link here. And that's it for us. So thank you to everyone who's helped, from Duke University and the Medical College of Wisconsin, and of course, Terry, for telling me about the SIIM Hackathon. And this is our team. So thank you, everyone.
Thank you very much. Judges?
I just want to say I really love this concept, and I really love the way that you've kind of tied in different aspects of the patient care flow, from the stroke team to the future concept of maybe communicating to the primary care physician. And I just a comment, that's all.
Thank you.
Thank you very much. That was team number 6, Mastermind from Marquette. Next, we have team number 7, SIIM. I hope I'm saying that right. The idea is to add an authorization engine to DICOM Web using some XCAI shortcuts from Nick Hermans. Nick, as soon as you're ready, please take it away.
Thank you very much. Can everyone hear me?
Yes.
Hello? Oh, yes. Let me just find my screen to share, because this is apparently not very easy. Let me see if I can share that. Do you see my screen?
Not yet. Yes, we do now.
Okay. So yes, I'm Nick Hermans. I'm from the Flemish Hospital Network KU Leuven, the Catholic University Leuven. I'm here to talk about my product SIIM. It's a magician spell, just like abracadabra, but it uses the word SIIM. I'm trying to achieve dynamic access and authorization to PACS resources using DICOM Web encapsulated by XCA. One of the big problems in sharing medical images is that there are not a lot of authorizations engines available for hospitals to allow access, to their PACS over the internet. In Belgium, we see this problem a lot, and I decided, during this hackathon, I'm going to work on something like that. So in Belgium, we have a couple of regional hubs. I author one of them. It assures that care providers and patients can access information of connected hospitals and radiologists and labs. There are 4 different hubs in Belgium. At the core, there is the Meta Hub. It's run by our central government that knows the locations where every patient have been in Belgium, and can manage consent and therapeutic links and therapeutic exclusions of patients. It's a kind of authorization hub. And it connects the different hub systems together. So around the turn of the millennium in 2000, the Walloon part of Belgium already created a standard or a system that could be used for sharing documents between hospital systems. During that time, the University of Leuven had a similar system that did not only share documents but also shared information regarding the entire care process of the patient. But during that time, there was no IHE profiles available, so it was all based on proprietary systems. How does that system work? Of sharing medical information. In practice, GP software vendors, they implement the hub system in a separate tab where they can see all the medical documents inside the Belgian care system. In practice in hospitals, they usually embed a kind of viewer that plugs into that system, and also provides patient portals to the entire repertoire of medical images available in the Belgian hub system. Also, hospitals can write their own custom software to interact with it. So each hub has a little bit of liberty on how they implement it. Externally, they have to expose the Belgian standard, but internally they can choose to do it with IHE standards, for example. So our hub is based on IHE standards. Many of the hubs follow the same approach. So they have a central index where you register documents on and where you can retrieve documents from. By the way, I'm trying to do a world record here by trying to explain XCS and XCA in 8 minutes. So cheer for me, please. Another way to approach this is to use on-the-fly querying to connect multiple institutions together using the XCA profile. Basically, it enables you to not to use one central registry, but to link multiple registries together and have a kind of custom implementation behind those registries and repositories. So that, with sharing with radiology images, what are the core problems with using, for example, XDS? XDS, the way that radiology images are stored on the XDS platform is using key object selection files. It doesn't support frame numbers, for example, and it does not. It's not easy because once you register one of these objects, the study is usually updated many times. For example, measurements are added to the study, key objects are added to the study, grayscale presentation states are added to the study, reconstructions, merges, and unmerges are done. So these key object files need to be constantly revoked and resubmitted on the repository to fix them. So there is a solution to that. And one of the solutions is the DICOM web. DICOM web is an API, so you can retrieve study list information on the fly, or retrieve raw DICOM files or rendered DICOM files if you want. The idea is then to deprecate the provide and register document set of COS objects on central registry and embrace XCA for dynamic, and extend it with dynamic responses. The way that we do this is to create a list of radiology studies on the fly with QDO RS or DIMC find. And then when a user requests the COS object, create it on the fly dynamically using QDO or cfind. Then abstract all these things behind the XCA interface so you can plug it into your XDS system. So I have a small demo. What I did was basically connect the SIIM VNA to our responding gateway server by reading the DICOM tags provided from the QDO RS responses for on an image level query and map them to a COS object and create it virtually, and also use the QDO RS responses for study list information and create XDS metadata from it. When you combine these things together and you put it in a responding gateway, you end up with the ability to, I'm going to open a patient record or medical record and open our hub viewer to demonstrate. Please work. So we'll open our hub viewer. It's XDS based. I will here is one of the studies that is detected from the SIIM VNA. I will open it using a action. It will open our viewer, and not sure if it's visible on camera. It says that error occurred while trying to load the image. It says Hackathon SIIM while the URI. The reason it's not working is because I did not implement the API key of the SIIM Hackathon on our production system. That was a little bit too cumbersome. So I have the same URL here in a paste. And I'm just going to paste it in my Google Chrome here. Or not my private Google Chrome. I will paste it here. Hopefully it works. Yes. I need to enable the API key, which is now public to everyone. There you go. I will show
2
me
minutes.
a breast image. All right, so originally I started, I wanted to implement a custom rule engine directly on top of CUDA-RS and DICOM Web that uses JavaScript to determine the access control so that hospitals could more easily enable access to their DICOM Web servers over the internet. However, I ran into many stops and problems along the way. So I decided to recycle the access control system inside my XDS infrastructure based on SACML and patient information policy systems. Are there any questions? Thanks for your attention. Did I succeed to kind of scrape XDS and XDA in 10 minutes?
Well, we'll let the judges speak for that. Judges?
Yeah, I think you did. This is Kevin. So if I understand, then you're doing XDS, but without a static registry that's populated sort of case by case. You're building it on the fly when someone asks. Is that correct?
So yeah, we're doing both of them. So we're doing both for the smaller hospitals and for the smaller non-enterprise PACSs. We build we let them register to central registry. But for the larger hospitals, we try to not do that because of the reasons I said. Yeah, and I build it dynamic based on the responses from either cFind, TIM cFind, or CUDA-RS, or other proprietary ways for retrieving that information. Sometimes we also use responding gateway queries if the PACS supports it, like a Fuji PACS, for example.
And do you have any thoughts on potential performance issues in doing it on the fly and on sort of data correlation issues? I guess when you find slight mismatches in records on the fly that might need sort of adjudication. Any thoughts on those?
Well, because we use the PICS profile and a kind of discovery system, we don't query PACSs if we know there's no data there, right? So we try to minimize the loads on the PACSs that way. And of course, small PACSs or small hospitals, they don't have a lot of patients visiting there, so they don't get a lot of queries. Of course, it's possible that the connection timeouts occur because PACSs might be remotely. We don't do a central big silo of PACS, but we distribute our PACSs. So yeah, there are some problems with that, but generally using smart caching and these things, it fades away. The benefits of having this system where you can share images freely on the internet in a secure and safe manner outweigh the problems of sometimes these images not being available, because if you don't do this, your images will never be available.
Mm-hmm. Cool, thank you.
Are there any more questions?
Thank you. That was Nick Hermans, team number 7, SIIM. Next, we have team number 8, interactive image segmentation for easier image annotation. It's a web app that can be used to support people through the annotation process with the use of an interactive image segmentation algorithm presented by Soterios. I'm going to butcher their name, Goutakandisas. Soterios, as soon as you're ready, please take it away.
Yeah, so can you hear me?
Yes.
Okay, cool. Yeah, so hello to everyone. Just a very short introduction about me. I'm a software developer. I have no experience with radiology and these kind of things. I actually found out about the hackathon 3 days ago, and I thought it would be interesting to come up with an idea and try to solve a problem. But of course, like in 3 days and being the only developer, it's not so easy. So anyway, I thought about, is there anything that I can do that solves a problem and I can present it in a nice way? And the idea that I came up with, let me start by sharing my screen. My presentation is not so professional as the other people, so you'll have to excuse me about that. So nowadays it seems like for whatever problem you have, you just develop a machine learning model, you train a model, and then you have your solution. But what?
So Tyrio, if you're sharing your screen, we can't see your screen.
Okay. No?
Yes, better.
Okay. So yeah, so like I said, it seems like nowadays for wherever there is a problem, you just train a machine learning model, and then you kind of solve your problem. But if you speak with people like data scientists, a lot of them will tell you that usually it's not so difficult to actually train an efficient model that does a specific job, but rather find quality data to train this model, because the precision of the model, how good it performs, highly depends on the quality of the data you use to train it. And most of the times, finding this data is difficult, and it also requires a lot of manual work, like going through the data and clean them and try to annotate them. And like I said, this can be very frustrating from time to time. And my idea was like, okay, maybe I can develop a web application that is easily accessible and supports the user during this annotation process by image data. And I'm just going to show you a little bit this GUI that I made in these past 2 days. So basically, the idea is you have this web application runs on the browser. You choose a file. You press this button, choose file, and you choose a file. And after you have chosen the file, it will appear here an input image. Now, of course, you see a flower. It's just for the presentation. Of course, radiology images can be used as well, but here it's just to make a point. So you choose the image, you see it displayed on your browser, and then you have on the right these seeds, these radio buttons. So basically, when you choose one of these, then you can go on the image and draw some strokes to give to the segmentation algorithm information what you consider to be an object of interest and what you consider to be background. Because if you were trying like to segment manually this a flower and like put an annotation on it, it's gonna be very difficult because of the shape. It's not so easy. So here the user needs only like to paint some strokes and say, okay, the flower is what I'm interested in, and the other things that are painted with a red color belongs to the background. So the algorithm knows what is foreground and what is background. And after you have finished with this, painting the strokes, which takes, I don't know, just a few seconds, I would say, you just press the segmentation button, and then the segmentation takes place, and you get your segmented image, and you have your segmentation mask, very good. And then you can use it like to annotate it without problems. So yeah, that is the basic idea. I will just show you here some examples how the algorithm works with some data. Not always will the results be good. This is a very basic implementation. I haven't optimized any parameters, just a very, very basic implementation. I will first choose the image that I showed you in my presentation. I chose the image. Now I go here, I choose foreground, and I say, okay, look, these parts, the pixels that have this color belong to the object that I'm interested in. I just mark some parts here to give information to the algorithm. Hey, this belongs to the background. And then I press the segmentation. And now the algorithm is doing the segmentation and you get the result. This is, I have to admit, an easy image. So the algorithm performs pretty well. And now I'm going to choose another image. I don't know, maybe this one. It's going to be a little bit more demanding, I guess. Just again, we just draw here a few parts in the background. Say, okay, look, here's the background. We press the segmentation. The algorithm takes around 5-6 seconds, depending on the image. But if the implementation is efficient, it could only last, it could take only milliseconds, for example. Now I'm going to choose another, a little bit more challenging image, just to show some limitations. And the final image will be a radiology image. So again, here you have messy. You just paint here and say, okay, look, this is what I'm interested in. And this is the background. And I press the segmentation. Here, probably the segmentation result will not be that good, but I have the possibility to go here and mark again, like see which part wasn't segmented so good, give a little bit more information to the algorithm, press again segmentation. And now with new information, hopefully the segmentation improves. And I'm just showing all this, like I said, because of the annotation difficulties that there are. So this algorithm could be used like for organ segmentation and for 3D organ segmentation for educational purposes as well. Here I'm going to show you the example in trying to segment the lungs.
2 minutes left.
Yeah. Okay. And here I'm going to say, okay, I'm not interested in this, Okay, so I will perform segmentation. Here is going to be, I'm guessing the result not so good. It's more challenging, this one, but the algorithm can further be improved. And then I can go here. Like I said, it's a very basic implementation. Foreground. I need to mark this here. Background. Again, here. And press the segmentation. Again. Takes a little bit of time, like I said. Yeah. So yeah, that is the idea, to provide a web application that helps the user to do the annotation as easily as possible using standard web technologies. Some of the things that I would like to do in the future is, of course, to improve the algorithm in terms of speed and precision. There are publications that can help me with that. And I just wanted to show you a little bit how a 3D segmentation could look, again, like for educational purposes. Let's say you have a tumor that has a certain kind of physiology and you would like to show to your medical students. Something like that would be possible with a segmentation algorithm that I just presented. And yeah, that's it, more or less, for my presentation. Yeah.
Thank you. Judges, comments, questions?
Question, I guess. So is the segmentation working off intensities or textures or edge detection?
There are different kinds of information that you can actually incorporate in the algorithm. Now I'm only using intensities, which is why in the last image it had a little bit of difficulty segmenting the lungs with a good precision. But in general, the more information I put into the algorithm, I combine into the algorithm, the better the segmentation, of course.
Mm-hmm.
All right. Well, thank you. That was team number 8, interactive image segmentation for easier image annotation. Thank you, Soterios. Next, we have a non-competing entry. Number 9 is a non-competing entry. It is called Snaz My Rad by Nick Hermans again. Nick, welcome back.
Thank you for having me a second time. I'm going to try to present my screen when you guys see, when everyone sees my screen. Please holler.
Yes.
Okay, thank you very much. So yeah, what I want to demo, there was a discussion going on saying that, look, medical imaging and healthcare is not always about sadness, about bad news. Sometimes it's about good news. And that really, you know, Dave gave an idea that said that why, you know, can't we just easily look at radiology images and just like make a puzzle out of it, or make a greeting card so you can print it on your printer or send it to Walmart or whatever and have them print out gift cards for nice occasions. Or just if you're on a skiing trip and you break your leg and you say you wanna share it on Facebook, right, with a small filter in front of it. So I did a kind of 10-minute implementation of an example of that. This is my medical records using one of our patient profile portals. I'm going to open, I tried to do it with my wife, but she's putting the baby to bed. So I'm going to use an echo abdomen of myself. Just pretend that it's a baby. And I'm going to just paste my code in here. I could not change our production system. I will get a file chooser. I can choose an overlay that I then can put over my image. And it's a baby girl. You can take a screenshot, print it on your printer, and you know, share with your friends and family. And have a good time with your radiology images. That's everything. As you can see, if we look at the code, because I don't want to steal too much of your time, it's very simple. And of course, it needs a lot of work to be put in our actual viewer. But yeah.
All right. Thank you, Nick. Judges, comments, thoughts, questions? Okay, well, thank you, Nick. That was team number 9, Snaz My Rad, is non-competing entry. So that concludes all 9 teams, 9 presentations for our Hackathon Showcase. I want to give a shout out to everybody who presented today. For the purpose of our People's Choice Award and for the judges to remember who everyone is, I'm going to tell you about them once more. Team number 1, the Trachea Tracker Portable app. Team number 2, Case Tracking Project. Team number 3, Rosa, Radiology On-Screen Assistant. Team number 4, PokeRad, Gamified Radiology. Team number 5 is from 1Qubit, Team 1Qubit. And that is the smartphone application for AI. Team number 6, called Mastermind from Marquette. Team number 7, SIIM. Team number 8, interactive image segmentation for easier image annotation. So thank you again for all the participants for taking the past 72 hours, sometimes more, to work so hard on your hackathon entries and to make the presentation and share it with us. Thank you for the hackathon committee for organizing and make this particular competition possible. Thank you to the SIIM staff who worked so hard behind the scenes to make sure these all go smoothly, and it has. Thank you for the mentors. Without you, again, most of these projects would not be as complete and as polished as they are. And these continue to be extremely high quality projects that we see year to year. Thank you to all your volunteerism. And lastly, to the SIIM community, whether you are watching this on recording in the future, or whether you're here with us today, it is based because of your support that the SIIM Hackathon gets to showcase these incredible projects from year to year and continue to share with the community. Anybody who is on Slack, thank you for participating. And this is Howard Chen. I am your moderator, and we are out. Thanks, everyone.